Hey guys, so this is Sumadhur again. This time we are going to try to solve uh, a minimization problem for Module B of Linear Programming from the 12th edition of Operations Management by Jay Heizer and Munson. Um, this would be problem number 27. The problem that we are given is let's bring down all the required information that we have to formulate the problem, such that we are talking about new brand of dog biscuits. One is chicken and the other one is liver flavored biscuit that meets certain nutritional standards. So let's see, if we were to talk about the chicken, let those be, so let x1 be the chicken flavored and x2 be liver flavored biscuits. The liver flavored biscuit contains 1 unit of nutrient A, 2 units of nutrient B. So 1 unit of nutrient A and 2 units of nutrient B. Okay, the chicken flavored biscuits, this was liver biscuits, and then 1 of A and 2 of B. So this is 1 of A and 2 of B. And chicken one has 1 of A and 4 of B. So 1 of A and 4 of B. According to federal requirements, there must be at least 40 units of nutrient A and 60 units of nutrient B. So let's say if you were to talk about nutrient A, we are given at least 40 units in the mix. So this has to be greater than or equals to 40 because it says at least. So even if this plus this is equals to 40, we are good. And then 60 units of nutrient B. So 60 units of nutrient B. Okay. Now let me draw this. And what else? In addition, the company has decided that there can be no more than 15 liver flavored biscuits. So x2 has to be less than 15 in a package, and it costs 1 cent to make one liver flavored biscuit and 2 cents to make chicken flavored. So this costs 2 cents, this costs 1 cent. Okay, what else? What is the optimal mix of the package to minimize the firm's cost? So if we have, the cost would be, if we were to make x number of chicken biscuits and x2 number of liver biscuits, then our cost function or the objective function would be 2 times x1 plus 1 times x2, and this would be our cost, and this needs to be minimized. Then whatever x1 and x2 comes out to be, the nutritional value in the package would be the number of biscuits in the package. Therefore it would be 1, let me pick a different color. So 1 times x1 plus 1 times x2 has to be greater than or equals to 40. This would be the nutritional value of A, so for constraint A. And then next one, the 4x1 plus 2x2 has to be greater than or equals to 60 as per the federal requirement for nutrition B, and x2 has to be less than 15. That's the condition, that no more than 15 liver flavored. So the rest of the number of biscuits in the mix would be x1. such that the combination of the nutrition A and B are met. Okay, now let's bring this problem in spreadsheet so then we can use solver to find out the x1 and x2s for us. So at this point I'm going to bring in view, new window, and I'm going to bring this here such that we can start solving this. So it's the same spreadsheet, but I'm going to bring this, oops, changes this as well. So this is good enough. So hold on, I want to keep this one the same, but I want to go this one sideways such that I can keep our hand notes close to us. So now we have chicken biscuits and we have liver biscuits. I will name this as x1 and this as x2, and I'm going to color these as yellow and name them as decision variables. Then I know this one sells for 2 cents and this one sells for 1 cent, such that same as before in the past problems, the cells to the left, the cost, comma, the decision variables, which gives us the number of biscuits, and I'm going to freeze this so then I can copy it later on for the constraints as well. Okay, and I'm going to keep this one as, let's say, green, so then I know this is my objective function when I'm using the Excel solver. Okay, now also then the constraints, I'm going to write it on this side because we know this the sensitivity report is going to pick up the first left alphabet. For nutrition A is 1x1 and 1x2. This is coming from this equation. Okay, so 1x1 therefore and 1x2, I'm going to copy this, Control C, and paste it as formulas, and I'm going to keep this one as blue so then I know this is my left hand side variable. Okay, so let me type LHS. This will go in the sensitivity report. As we know, the Excel will try to be smart, and the given right hand side variable is 40. And this time we are given that the total number of nutrition A in a package has to be at least 40. So we are going to use greater than or equals to 40, which we did put down here. Similarly, the constraint for nutrition value for B is see 4x1 plus 2x2 greater than 60. Okay, so it's 4x1, 2x2, and it has to be greater than 60. Also, x2 has to be less than, and I'm going to show you why am I doing this. So 0 for x1 and 1 for x2, this has to be less than or equals to 15. So let's see what this does. So for this one, it's some product of 1 times x1 plus 1 times x2. So what it is doing is it is doing 1 times x1 plus 1 times x2, and it stays here. It gives us in the blue cell. Similarly for this one, it says 4 times x1 plus 2 times x2, is shown in this cell. Okay, so if we were to click here, that's what it does. Yeah, decision variable cell stays the same. Now what it does for this one is 0 times x1 is 0. Okay, so that is for this one here. Since we have nothing for x1 here, but 1 times x2, so x2 is coming from the top here, yeah, from the decision variable. So our x2 is here, so 1 times x2 is x2, has to stay less than or equals to 15, so that does the job. Okay, now we only have one more condition to make sure that x1 and x2 stay positive or 0, such that there's no such thing as negative number of chicken biscuits. So let's check our calculation. Let's say if I make one of each, then all of these cells in blue should change and make sense, such that we make 2 times 1 plus 1 plus 1, 1 times 1 is 3 with that, and this is the cell that we want to minimize. At the same time, 4 times 1 plus 2 times 1 is 6. That is correct. So our calculations seem to be correct, and we are ready to use the solver now. Okay, so let's maximize this such that we can see it a little better, and we're going to go to data, solver, and make sure our set objective is this green cell. We want to minimize this by changing the variable cells which are in yellow. Add these two conditions are similar, so I'm going to choose them together, that 2 and 6 have to be greater than and equals to 40 and 60 respectively. Also this one, the last condition has to be less than or equals to 15. Yeah, this time hit OK, make sure that this is checked. This takes care that x1 and x2 are non-negative, which means 0 or positive, and we choose simplex LP, and then we hit solve. So once we hit solve, we make sure that you keep it on keep solver solution. Now one thing I noticed that I forgot to give this a name, so let's see what was the condition name. Oops, the condition name was, let's say, there can be no more than 15 liver biscuits. Yeah, so this one, let's say we name this as max liver biscuits. Okay, so at this point, oops, okay, at this point we go back, which we've already solved it, but this time, in addition to keeping the solver solution, we are also going to create the sensitivity report, okay, which has been created here. Okay, the latest one. So first things first, it says that we should make 25 chicken biscuits in a pack and 15 of liver biscuits. Now make sure, if you see, it's all coming from this third constraint. Otherwise, I'm sure this is what's limiting, and this seems to be the binding constraint. Okay, now let's check if that is really the case, such that I want to bring this here, and let's see if we bring the other spreadsheet, such that we can look at this. Okay, so the sensitivity report 5, so sensitivity report 5. Now let me bring this like that. So now that we have used final value 40, and right hand side constraint was at least 40, so we have stayed on the lower side of the constraint. So if you look here, we said the nutrition value for A, the collective nutritional value for A has to be at least 40. Okay, and that's what we've done. And also we said that nutrition value for B has to be 60. Now 60 was the required minimum, but we are we are putting in 130. Why so? um, uh, at the same time, the maximum liver biscuits, this is not fully visible, okay, that there has to be no more than 15 biscuits that are of liver flavor. So the final value is maximum 15. Now here you'll see the shadow price is 2, which means the way we would interpret that is that is if you were to relax your constraint, which means if you were to relax your constraint of 40, now this is minimum, right? So the relaxing the constraint would mean 39. If you were to relax the constraint by 1 unit, you can improve your solution, which improve your objective function by 2. Now since our objective function in the cost of cents, that means improving the objective function would mean that we can get this to 63. Yeah, 63. Okay, so let's see if that would be the case. So based on this sensitivity report, if you were to relax our constraint, so going by the definition that I gave in the first video, if you were to go shadow price is the amount by which if we relax the constraint by 1 unit. So relaxing the constraint, in this case this is greater than 40. So on the upper end this is infinity, on the lower end it is limited at 40. So we can only relax it by 1 unit to make it 30 as the right hand side. That means if we were to do this by 1 unit, then our objective function improves by the amount of shadow price. Okay, so our objective function is minimization of the cost. Therefore improving that would mean that we further reduce it down by 2. So let's see if that is the case. If you pay attention here, from 30 I'm going to make it 39. Oh, sorry, from 40 I make it to 39. So I relax the constraint by 1 unit. And if I was to solve, then our cost goes down to 63. Okay, so I'm going to bring it back to 40 and then solve it again to bring it back to this thing. We'll come back to 65 again. Okay, so hit solve and keep solver solutions. That's it. Now the shadow price for liver biscuits, the third constraint is -1, which means if we were to relax the constraint, okay, which means relaxing the constraint would be if we were to go from 15 to 16. Yeah, that would be relaxing constraint because it is bound on the upper side. Okay, so the allowable increase and decrease. Now in terms of allowable increase, on the upper end this is not limited, so on the upper end it can go as much as it can, so that's why allowable increase is infinity, and that's how the spreadsheet represents this. Allowable decrease is 17.5, so it can go 40 minus 17.5, so this minus 17.5. Also the allowable increase for the 60 is only 70. Allowable decrease is as much as possible. Now for the last one, the allowable increase is 25 and 15, so it can go from 15 plus 25, and the decrease is 15 minus 15, which is 0. Okay, so the range is 0 to 35 15 and 25, 40. So 0 to 40. Okay, now I think that's about it. We've gone through everything possible. Allowable increase, we also know for the variable decision variable E14, it's this one, and the allowable increase is 1. So the coefficient for this is decision variable is 1. So it can go from 1 cent to 2 cents. The decrease is infinity, which means the lowest we will take is 0. And that's about it. Have fun.